That was your good evening. Good evening. That was your major chunk of investment, Muhammad Umar. Yes. No. Okay. Ethereum. Okay. Major chunk is an Ethereum. Okay. What about other altcoins? I mean, like very. Do you have you also invested in Doge, the Dogecoin, or coins like that?
No.
No, no, not coins like that. Okay. Why is my thing? Okay, it is charging. Battery is not charging. Write the topic: Gibbs free energy. Topic: Gibbs free energy and equilibrium. Yes, our last topic was entropy. We also did Gibbs free energy. Na? See, our last topic was not entropy exactly. It was Gibbs free energy. Okay. So now we are writing about Gibbs free energy and entropy. Sorry, and equilibrium, not entropy, and equilibrium.
Okay, sir.
And equilibrium. Equilibrium. Okay. All right. The relationship, it has been just stated like this for you guys. Okay. There is no derivation for you. So delta G is equal to, for a reaction at any condition, that means the Gibbs free energy of reactions, the change in Gibbs free energy of a reaction at any condition, it is equal to the change in Gibbs free energy at standard condition plus RT ln Q. This is the general reaction. What is Q? Q is the reaction quotient. Reaction quotient. What's the spelling of quotient? QU OTIENT, no? OTIENT. Reaction quotient. What does that mean? For a general reaction, that is A, that is the stoichiometry of the reactant A plus the stoichiometry of reactant B is small b. It is giving you AA, sorry, not A, it will be giving you CC plus DD. Okay. So if you have a general reaction like this, then the reaction quotient Q, it is given as the, it is the ratio of
RT, EN?
ln, the natural log. So the Q is given by CC D to the power of small d, A to the power of small a, and B to the power of small b. Okay, so this is what, I mean, you can say it is products to the power of their stoichiometric coefficient upon reactant, the concentration of reactant to their stoichiometric coefficient. Right? This is the general reaction. If you, this is the general thing. If you have delta G, then this is equal to delta G naught plus RT ln Q. RT ln Q. Now at equilibrium, things change. Now at equilibrium, when nothing is happening, right? At equilibrium, nothing is happening, right? So when delta G is positive, the process is non-spontaneous. When delta G is negative, the process is spontaneous. When nothing is happening, when there is no process, delta G is equal to 0. If nothing is happening, then there is no change. If there is no change, that means delta G will be equal to what? At equilibrium, nothing happens. So delta G is equal to 0. And we write Q is equal to what? There is a special character. There is a special letter for the reaction quotient at equilibrium, that is K. That is K. It means the same thing. Okay, what is K? K is the reaction quotient at equilibrium. Reaction quotient at equilibrium. So when delta at equilibrium, delta G is equal to 0 and Q is equal to K, we can write that delta G naught, it is equal to minus of RT ln K, minus of RT ln K. You can also write delta G naught, it is equal to 2 point minus of 2.303 RT log of K. A side note, ln, it is equal to log with a base E, and when I write log like this, it means log with a base of 10. Okay, write this down. Let me know if you're done. Then we will move to the chapter equilibrium. हाँ, आप बताइए क्यों minus? You see the previous reaction and figure it out. Delta G naught है. Figure it out, Atif. It's easy. You got it?
Yes, sir.
Okay. Done, all of you? Please let me know if you're done.
Wait.
Okay, okay. So then let me just keep writing that. So I can also write delta G naught. It is equal to what? Delta H naught minus T delta S naught. And this will be equal to what? Minus 2.303 log K. Done, guys? That's the most praise I can get. Thanks, Umar. Thank you, thank you. Okay, who else remaining? Is everyone done? Is everyone done, guys?
Yes, sir.
Okay. Okay. So now I think everything is completed in your thermodynamics. Yeah, I think everything is completed in thermodynamics. Now we are going to do equilibrium. Okay, we are going to do equilibrium. Now I will start with a general sense what is equilibrium and where. Okay, I hope you remember where equilibrium lies in our chapters, right? Where equilibrium and thermodynamics they lie in the different chapters that we have in our NCERT, right? We started with simple stoichiometry, how to do science. Then we went towards atoms, and then we went towards some basic more properties of atoms, okay, and how they have what type of valency is there and how they interact with other atoms and how do they form bond, how do they form molecules in chapter 3 basically, and then chapter 4 what is the bonds, and then in states of matter how if we have a large system, then how are these going to behave. We looked at the what is the behavior between atom, that is a bond. Then if you have a molecule, then we have, if you have a molecule, then the intermolecular forces of attraction is somewhat present. Tutorial on Friday. I'm thinking about it, Surat, okay, because we have done many problems now in this chapter. I did not leave any numericals. So I'm thinking whether we should do a Friday tutorial. I think we should do, but we will see. I don't know as of now. Wednesday, if I tell you on Wednesday, that will be fine, no? If I tell you on Wednesday. So intermolecular forces of attraction, and after that we went to thermodynamics, and now we are going to equilibrium. Now we saw somewhat equilibrium in the thermodynamics chapter, that there is some initial state, then we do some change, then there is a final state. There is some process, rather not change, it is a process. We do some process, and there is then final state. So equilibrium is maintained here also. There is equilibrium here. Not much thermo is required to understand equilibrium. Not much thermo is required. Okay.
Okay, sir.
You need the basic ideas, but obviously you need some basic idea like what is delta G, what is delta H. These things may come. So you just need to know these terms, nothing else. Now in final state, we also will have equilibrium. Okay, we'll also have equilibrium. Now there's some process which happens. Now what we are going to study, we are going to study what are these states, Okay, so initial state, then there will be some process, and then the final state. And then we will talk about what is equilibrium. So let me take an example like this. We have a box, and I have separated this box by some barrier. Okay, and some barrier, and this barrier is what it is? Adiabatic boundary. Adiabatic. Okay, that means the exchange of heat is not possible. Q is equal to what? 0. Exchange of heat is not possible. Okay, we have two compartments here. In one, we have some blue gas molecules. And here we have some red gas molecules. Okay, let us say the temperature of these molecules is 50 degrees Celsius, and the temperature here it is 20 degrees Celsius. Okay, so this is the initial state. All of you, yes or no? Initial state, yes or no, guys?
Yes,
Tell
sir.
me.
Yes.
Any problem till here? No problem.
No,
Now what
sir.
I did, I removed this barrier. What will happen if I remove this barrier? These gas are not, they are non-reactive. Okay, they will not react with each other. Then what will happen? They will mix with each other. Yes or no?
Yes, sir.
They will mix with each other. Okay, they will mix with each other. Now, when they are mixing with each other, what is the change you will see? What is the most important change you will see? You will see that if you place a thermometer here, and when these gas are mixing, you can say that there is a change in temperature. Yes or no? The temperature will start changing. Correct?
Yes, sir.
Yes. Okay. Now, will the temperature keep changing, or it will come to a point where it is not changing? Will it become constant at a point, or it will keep changing?
It will become constant interval.
It will become constant to a point. That means till the time the temperature was changing, we were having some process. Now, after a while, what happens? It reached a point where the temperature was not changing. So delta T was 0. When the temperature was constant, we said that it reached a equilibrium state. Now you understand what is equilibrium? Yes or no, guys?
Yes, sir.
Okay. Now this will be a constant theme.
Sir, can you repeat again in brief?
Okay. So we had a gas, and there was a barrier, adiabatic barrier, in which heat cannot be transferred. Okay. So if I am placing a barrier here, that means the temperature from here, it cannot go from here to here. Okay. If I'm placing the barrier, that means this is 50 degrees Celsius and this is 25 degrees Celsius. And after that, I remove the barrier. And as soon as I remove the barrier, what will happen? The gas will start mixing with each other. And when the gas will start mixing with each other, the temperature will also start to change, right? Because here we have 50 degrees, here 20 degrees Celsius. So when they will mix with each other, the temperature has got to change, right? Temperature will change, but it will not keep changing for it will not be changing at all times. It will stop after a while. The temperature change will stop after a while, and that state, we will point that when the temperature has stopped changing, that is the equilibrium point. At that point, the equilibrium has been achieved. Okay, so this will be a general theme in our chapter. We will have some initial condition. Okay, and then we will do some change. Okay, then we will change something, and then we will get the final state. Now, initial को हम लोग initially बोलेंगे. We will say initial is initial. The change will be change. Okay, and the final we will say that it is equilibrium, the equilibrium state, because after that we are not going to change anything. That is why we will say that now it has reached the equilibrium. So we will be revolving around this idea of ice, that we will see some system initial state, then we will see some change in that system, then we will see what is the equilibrium. Okay, what is the equilibrium? Now, the initial state, it will also be the initial state. We will have some state variable. That state variable, there should be some state variable here. Okay, similarly in the equilibrium also there should be some state variable. In the equilibrium also there should be some state variable. Now that state variable, in the previous example it was temperature. Now at equilibrium here also we will see the temperature. Now the temperature should be constant. There should be some property at equilibrium which is constant. Okay, there will be at least one property in equilibrium which is constant. Okay, now please write with me. You have to know there are two types of equilibria that we are going to study. We have classified equilibrium into two types. There is something that we have to study and something we don't have to study in very much detail. There is physical equilibrium that we don't have to study in much detail. Physical equilibrium. Now in physical equilibrium, you can have liquid which is in equilibrium with vapor. Okay, liquid which is in equilibrium with vapor. Now let us look at this system, liquid and vapor equilibrium, and let us see what is the property that is going to be constant. What is the property that is going to be constant? Okay, now I ask you one question. You have water here. Okay, you have some water here, not this much water, very less water in an open vessel. You have some water here. Okay, then you have an open vessel and a closed vessel. Now you guys tell me, in which of these vessels the evaporation will be faster, the closed vessel or the open vessel? A or B? Where will be the vaporization faster?
A.
In A. Why?
Because
Why A?
it's closed.
So it is
The
closed.
heat
I
will,
can
the heat
heat.
will not.
How many of you can explain me evaporation? Just leave this. Who can explain me how evaporation happens? Yes. Okay. If no one is going to explain to me, then I'm also
After
not going to explain.
boiling the water.
Boiling the water.
Yes.
If you splash some water on the floor, it will not evaporate. Huh, Muhammad Umar? I'm not asking about boiling now. I'm asking about evaporation. Tell me how evaporation happens.
Evaporation happens when the water like the temperature is below 100 degrees Celsius.
No, I'm asking how does it happen? What happens? Wait a second. What happens in evaporation? We have H2O, liquid. It gets transformed to H2O, gas. Okay, very good, very good. Okay, Abhinav, what did you say? What did you say? Heat, right?
Yes, sir.
Heat. It happens due to heat, right? So what you are saying, we are heating the water?
But below 100 degrees Celsius.
No, but water gases is only present at 100. You cannot have gaseous water na, below 100 degree.
Yes, sir.
So how it is
like the
getting converted?
temperature is below 100 degrees Celsius. Not of the water, of the environment.
Okay, so I am asking, you are heating the water, na? Yes or no?
Yes, sir.
You're heating the water. Now you're heating the water to what temperature?
100 degrees.
You are heating the water to 100 degrees Celsius. And this is how evaporation happens. You heat the water to 100 degrees Celsius and then you get H2O gas. Yes, Abhinav?
Yes, sir.
Okay. Now, before going to 100 degrees Celsius, kabhi to aisa time aayega hoga na, jab it will be somewhere around, let us say 70 degrees Celsius or 80 degrees Celsius, this water?
Yes, sir.
Okay. Have you ever touched the water which is splashed here and there? Is it that heated up?
No, sir. It doesn't feel like it's heated up.
So, why? So, we are not heating it, na?
Yes, sir.
Obviously, you can also say that if room temperature is only 25 degrees Celsius, then how can you heat something with more than 25 degrees Celsius, right? Because if you heat something more than 25 degrees Celsius, then the flow of heat will not be from 25 degrees Celsius to 70 degrees Celsius, right? It will be from
Yes,
70
sir.
to 25. So heat is not the answer. What is happening then? Who will explain me how evaporation happens? Now no one will say heat, okay? हम बार-बार ये चीज नहीं समझाएंगे. It is not getting heated up. Yes. Rihab, Nida, Muhammad Umar, anyone? Evaporation.
Is it convection, thermology?
नहीं. You explain it. क्या बोला आपने? That you are using too much jargon. Explain me in simple words. Na? Evaporation, it is not a very. When the water heats, it will turn into water vapor. When liquid turns into gas. अरे ये क्या बात है? Umar Abdullah. हाँ. Atif, you are saying something?
It's a terminology like the molecules are vibrating.
Molecules are no. Again, you are saying about heat only. Na? If molecules will vibrate, what will happen? The temperature will increase. है ना?
Yes, sir.
But we are not heating it actually. Na? At least that much you should be clear that we are not heating it. Acha. Can I give you this as a homework to tell me in the next class how evaporation happens? Can you do your own research? Can you look around here and there?
Okay, sir.
Okay.
Sir.
Abhinav?
Yes, sir.
You have to explain through water cycle. Are नहीं भाई, वाटर साइकिल में इवेपोरेशन होता है क्या? बाल्टी में पानी रहता है उसमें भी इवेपोरेशन होता है. I'm not talking about the rain cycle, okay? I'm not talking about the rain cycle. Yeah, evaporation, simple evaporation. If you splash some water on the floor, the water is evaporated after a while. You don't see any water. Why is that? Why is that happening? We are not heating it. Why is that happening? Okay. So let me just. So heating is not the. Okay, I need someone to answer me. If you have an open vessel and you have water here, okay, and you have a closed vessel, you have a water here. Which will get evaporated fastly, A or B?
A.
A. Is there anyone who thinks it is B? B will get evaporated fastly. It will get more rapidly evaporated. Is there anyone who thinks B? Atif, you want to say something?
No, sir.
No? Okay. What about others? Nida, are you there? Rihab, Surat? Surat, are you there? Rihab, can you turn the mic on?
Yes, sir.
Do you have anyone at home right now?
Yes, sir.
Who is there? Is your mom there?
No.
No. Is your elder, if you have any elder sister, is she there? Is your dad there? Anyone who is elder to you?
Yeah.
Yeah, ask them. Which will evaporate faster? A or B? पानी को खोल के रखेंगे तो जल्दी उड़ जाएगा या बंद करके रखेंगे तो जल्दी उड़ जाएगा? पूछ के देखिए. सूरत, can you turn the mic on? Surat, can you turn the mic on? I am seeing your chats. Surat. Yes, are you there? Surat? No. आप लोग का रियलिटी से मतलब वास्ता ही नहीं है क्या? है ऐसी, मतलब ये तो इतना आम सवाल हमने किया है. Either you live in the internet world more than the real world, that you don't know what will happen and you are confused. Surat, you can't turn the mic on. Surat, you also ask someone in your home. पानी कहाँ पे जल्दी उड़ जाएगा? खुले बर्तन में या बंद बर्तन में? Reba is coming now. I will ask Reba. Rehab, did you ask? Yes, Rehab, did you ask? Rehab, what I'm asking. Did you ask anyone? Yes. हाँ, ठीक है. Okay. What about you, Surat? So you have changed your answer now after asking. Yes, Umar. Okay.
Good evening, sir.
Good evening. Reba, एक सवाल है.
जी.
खुले बर्तन से पानी जल्दी उड़ जाता है या बंद बर्तन से?
खुले.
Okay, very good.
Sir, can you scroll up for me to take screenshots, please?
नहीं कुछ इसमें कराया हमने. आप स्क्रीनशॉट कहाँ का लीजिएगा हम बता देते हैं आपको. एक सेकंड. You take a screenshot from here. You take a screenshot of this part.
Okay, sir.
सूरत किससे पूछा आपने? Whom did you ask, सूरत? Yes, Surat, whom did you ask? No one. Rehab, whom did you ask? आपने किससे पूछा? Rehab, sister, okay. Done? Reba, can I go back? Equilibrium, okay. Fine. Now, if you have, when we have established that if you have a closed vessel, then the evaporation will be slower. If you have an open vessel, then the evaporation will be faster. Then the evaporation will be faster. Now let us take some special example. We have a system like this, and in which we have some water like this, and then we have another system. Okay, rather we should say take the system only. Okay, should take the system only. This is the initial conditions I will write initial. So initially, what is there? The water is present here, and we have some water vapor molecules like this. We have some water vapor molecules, and due to this water vapor molecules, there will be some pressure, right? This is the P of H2O. Okay. Now this pressure the pressure that is due to the evaporated liquid. Due to the evaporated liquid, it is known as the vapor pressure. Okay, it is known as the vapor pressure. This is something that you will read a lot in the 12th standard, vapor pressure. Okay. As of now, we will just see that this is the pressure of water, because that is H2 is vapor here. Now I did some change. Okay. Initially we had PH2O. We did some change. Okay. I increased the volume. I increased the volume of the system. Okay. I increased the volume of the system. Now what will happen to the pressure? It will increase or decrease. If I have increased the volume, you have learned the states of matter, right? What will happen to the pressure? It will increase or decrease if we increase the volume. Guys, tell me. Pressure and volume are inversely proportional, directly proportional?
They're inversely proportional.
Inversely proportional, right? So let us say this is time. Okay. And what I did, the pressure of H2O was something initially, right? It was constant. It was going on like this. Then what I did, I increased the volume. Then the pressure will drop like this, right? The pressure will drop like this. Now, slowly, what will happen? Slowly, what will happen? All these gaseous molecules which are present here, all these gaseous molecules which are present here, they can move upwards, right? They can move upwards, Hannah. They have got more area.
Yes, sir.
Now, when they will move upward, what will happen? There will be some vacant space left here, and there will be some more molecules of water which will be formed, right? More molecules of water will be getting evaporated, right? Now we have more H2O molecules which are evaporated because we know that the volume has increased. Now slowly, they will be covering up the whole volume, right? They will be covering up the whole volume. Now when we are increasing the number of moles of what is happening? The H2O molecules. Okay, if I say H2O molecules, I am saying the number of moles of H2O is increasing. Number of moles of H2O is increasing, and we know that the number of moles and the pressure, they have a direct relationship. That means the PH2O will also slowly increase. Now slowly with time, what will happen? The pressure of water molecule, the pressure inside the system, it will also increase, and it will attain the same equilibrium position, same equilibrium state, same state, right? So what happened? This was initial stage. Then here we had some change. Then some things happened, but eventually the system tried, and system went on to attain the same equilibrium state. Okay. Now what is this equilibrium? In this equilibrium, the P of H2O is constant. Okay. So as we can see now, what is constant? The pressure of H2O is constant. So if you have liquid vapor equilibria, then what is constant? Pressure is constant. Right? The pressure is constant. All of you understood this whole thing? Initial change in the equilibrium? Yes or no?
Yes, sir.
Yes, sir.
All of you understood this now? Okay, fine. So we will be thinking in this pattern only, okay? We will be, first of all, there will be some initial state. We will be having some state variable there, right? Then we will be doing some change, and due to that change, there will be some change in the state variable, but eventually what will happen? It will achieve some equilibria. It will achieve some equilibria, okay? Now that equilibria may not be the same equilibria as the initial state. It may be something different, but there will be an equilibria. We have to learn about that equilibria after the change. Second is we can also have solid liquid equilibria. Now in solid liquid equilibria, what will be constant? The melting point will be constant. If we have solid and liquid equilibria, the melting point is constant. The temperature at which a particular solid, it turns to liquid, okay? The melting point is going to be constant. The third point is, if we have solid, okay, that is S, or rather I should say like this. Let me write solute. solute and solvent. Solute. Okay, it can be in equilibria with, this is solid solute and solute in solution. Okay, solute in solution. Now what will happen? Let us say we have one glass of water. Sorry. And we put in some sodium chloride NaCl salt. Okay, NaCl salt. So can anyone guess what will happen? What will happen? The NaCl will be getting dissolved, yes or no? In the water.
Yes, sir.
Okay. So what is changing in the system? What is changing in the system? Is the temperature changing of the system?
No, sir.
What is changing? Is the what is changing then?
Nothing is changing, sir.
Nothing is changing. The concentration is changing, na?
Yes, sir.
Concentration is changing, है ना? So you have to think in those terms. Okay. Now slowly. Now you will get some practice, and you will. Now I said concentration is changing. So you will look at a system, and then you will be able to think what is going to change. Okay, what is going to change? So we will say that concentration is changing. Now, will the concentration keep changing if I have added one time and I close the lid? I added NaCl and close the lid. So the concentration will keep on changing?
No, sir.
No, it will stop at a time. No, it will stop at a time. So we added NaCl, and then what happened? The NaCl got dissolved. NaCl got dissolved here. Okay. So in this case, what is happening? We are having solute, which is solid. Initially, it was solid. Then we added it in the solution, and then it became in the aqueous phase if you are adding it in water. So solute in the presence of solution, I'm writing. And here, what is getting constant? Here, the concentration is constant. At equilibria, what is constant? Concentration is constant. I'm not talking about in the process, okay? I'm not talking the initial and final concentration is constant. I'm saying that at equilibria, we are going to look at the property, that is the concentration of the system, which is going to be constant. If you are looking at solute and solute, that means solute solid and solute solution equilibria. These are the physical equilibria that we will be dealing with. There will be some other that most of the time we will be talking about is the chemical equilibria, okay? In chemical systems. Equilibrium or equilibria in chemical systems, okay? So please write this much, physical and chemical. We will be more dealing with chemical equilibrium, okay, from now on. You don't have to worry about physical. It is not much there in your syllabus, okay? Not there in your ये also क्या बोलते हैं आपका NCERT also. Write this down. Let me know if you're done. Okay. Okay. Now, the story of chemical equilibria, you know, it starts with a very historical figure. It starts with a very historical figure. Now, how many of you remember the class 9th or 10th history book? Do you remember something? What was there in the history book? 9th, 10th class?
So French Revolution.
French Revolution. Okay, fine. Can you? Yes, French Revolution. What did you say, Reba? French Revolution, Reba. हम सुन ही नहीं पाए क्या कहा रीबा ने. Mohammed Umar, can you give me a brief idea what was happening French Revolution, and do you remember it a little bit? No. Yes, Muhammad Umar. Anyone remember something about French Revolution? Yeah, French Revolution.
Yes, sir.
No?
I remember thoda
You
thoda.
remember? अच्छा बताइए फिर.
Sir, in French Revolution, in the starting, the people overthrew the monarch and formed their own constitution
Association.
and stuff.
Okay. Okay. Then
Then,
what happened?
then after that, some group was there. I don't remember their name.
Mm-hmm.
They took over the
They
government.
Jacobin.
Jacobin Club,
Yes,
right?
sir. Jacobean Club.
Okay, Jacobin Club. And after that?
After they took over the government, the neighboring places which were there, the neighboring states,
Mm-hmm.
they attacked and took over the Jacobean Club and gave the rights back to the monarch.
Mm-hmm.
After it
Okay.
went back to the monarch, then I don't remember, sir.
Then you don't remember. Okay. So any, what I can say? Uh, any one king or leader that you remember after the French Revolution?
Enamel second.
And after the French Revolution, after the Jacobins and all.
The Napoleon?
Yeah,
Yes,
exactly.
sir. Napoleon.
Napoleon, right? Napoleon. So Napoleon, he conquered many areas, right? Many areas.
Yes, sir.
And with like when you are conquering something, no, then you take many people with you. If you are a king and you are conquering something, for example, like in modern day and time, if you have a state, so the state has many helpers around it. So they will have some people from administration, and they will also have some, nowadays, for example, they will have some people from the marketing department, digital marketing also. Now at that point of time, there were scientists who accompanied many kings when they were conquering many other their lands. So while Napoleon was around, some his army was some parts in Egypt or African area. He was there was a scientist with him. His name is Bert Howlett. I think it is double L-E-T. Bert Howlett. Okay, Bert Howlett. Now there is a very dangerous lakes. If you have any time now, then you may see in the YouTube Narton Lake. Narton Lake. Okay, Narton Lake. He saw something very क्या बोलते हैं, very surprising thing in the Narton Lake. What he saw was that there was some salt. When you have lakes. Yes.
Sir, it is
Natron.
red in color.
Not Natron Lake. Sorry, yeah, Natron Lake. Natron Lake. Yeah, it is reddish in color. Yeah, it is reddish in color. And yeah, what I was saying.
Salt.
It was salt.
Yeah, I was talking about salt, right? I was talking about salt. Now he saw some salts. He saw some salt in the Natron Lake. Okay, he saw some salt in that. I think that was Na2CO3. I don't remember exactly. I think it was Na2CO3. Like, give me 1 second. I think I should reconfirm this. If it was Na2CO3, and I can give you the reaction, then it will be better. Yeah, correct. So he saw that there was Na2CO3 present, like on the banks of the lake, and this Na2CO3 was only present where you had some CaCl2 also. Okay, some CaCl2 also. That means he was thinking that if Na2CO3 is present and CaCl2 is present, right? CaCl2 is present, and there was also some CaCO3 which was present. Okay, CaCO3 present. Now, when you are a chemist and you see these three entities, Na2CO3, CaCl2, and CaCO3, right? They were present in one area. Okay. So he was amazed because if you have Na2CO3, CaCl2, then all the Na2CO3, it should have been converted into Na2CO3, should have reacted with CaCl2, and all of these should have been converted to NaCl plus CaCO3, right? But it was not like that. There was traces of all these molecules present in the Norton link. Now, at that point, this idea came to him that it is not only that Na2 plus CO3, it is if you react Na2CO3 with CaCl2, it forms sodium chloride and CaCO3. The other way around is also possible, that if you have NaCl plus CaCO3, then it can also form Na2CO3 and CaCl2. Now, this was the beginning of reversible reactions. Because this is the reaction he saw in his lab, essentially speaking, and this is the reaction that he saw in the natron lake. Okay. Now, this was the beginning of reversible reaction. He said that this type of reaction, they can move both forward and backward given what is the condition. So essentially, initially what he said, that it depends on whose concentration is higher, whose concentration is very much higher. So what he said, that let us imagine like this: we have two plots. There is a reactant here and there is the product here. Okay, there's a product here. So whatever concentration you take for reactant and product, they will react with each other, and they will get to a point where some reactant is there and some product is there, and that will be the most stable state for both of them. And at that point of time, the reaction will going to happen. The reactant, it is getting converted into product. Some product is also getting converted into the reactant, but there is no considerable change in the concentration of the reactants and the concentration of the product. It does not mean that the reaction is not happening. The reaction is happening, okay? But simultaneously, what is happening? Simultaneously, you are forming NaCl and you are reacting with CaCO3, and you are forming Na2CO3 and CaCl2. But again, Na2CO3 and CaCl2, these are also reacting and they're forming NaCl and CaCO3. So both these reactions are what? Both these reactions are happening at the same time. Both the reactions are happening at the same time, but the rate at which it is happening, the rate is same. Now, let me give you an analogy. Let us say that you have a swimming pool like this. Okay, you have a swimming pool. Now, a person came to you and he said that in the swimming pool, if you look at the swimming pool, then there are 5 persons at a time. There are how many persons? 5 persons at a time. What does that mean? There are the same 5 persons all the day, or the 5 persons change, but on an average, you have what? You have 5 persons. That means if some person leaves, then the same number of persons, they come to the swimming pool. Okay, they come to the swimming pool. That is why what is happening? 5% is a constant. 5% is a constant, but the process is happening, right? Some people are leaving, some people are going out, some people are coming in. Similarly, the reaction is going on, but the concentration is what? The concentration of the reactant and the product is same. And it also does not mean the concentration of reactant and product will be equal. Okay, the concentration of reactant and product is constant. Concentration is constant, right? And concentration is same. These are very different. The concentration is same. These are very different. These are what? Very different wordings. If concentration is constant, that means the concentration is not changing. This 5% is 5%. And here there can be 7%. Now, this 7% is always 7%. It is not changing. This 5% is always 5%. It is not changing. But the rate, but there are some people coming in, there are some people going out. Okay, do you understand this analogy with the chemical reaction? Yes or no? Reactants and products. Tell me, guys. Yes or no? Abhinav,
sir.
Atif. Yes. Okay, fine. Reba, Surat, Rihab. What about you guys?
Yes, sir.
Yes, okay, fine. So this is how equilibrium is established. This is how equilibrium is established. Now let us write. First of all, I will define what is a reversible reaction, you know, because we have not seen reversible reaction till now. Then we will define the equilibria. Okay, so please write a reversible reaction. Reversible reactions. The reactions in which products that are formed can also react with each other under suitable condition to give back the reactants. Okay, write this down. Let me know if you're done. Rehab is done. Surat is also done. Okay, I think everyone is done. You can write examples, okay? You can write some examples. H2 plus I2, they can convert back to HI, 2 moles of HI, okay? Similarly, you will have N2 plus 3H2, they can form NH3, they can form 2 moles of NH3, and also the NH3 can get dissociated back to N2 and 3 hydrogens. Then you will have N2 plus O2, which will give you 2NO. You can also have 2NO2. It can give you, it can dimerize and it can form N2O4. And dimerize and it can form N2O4. Done, all of you? Done?
Done, sir.
Okay. Now write attainment of equilibrium. Attainment of equilibrium. Now, attainment of equilibrium. When we will say that the equilibrium has been attained. Okay. Then we will say the equilibrium has been attained. यहाँ पे देखिए, यहाँ पे क्या था? Initially, when we were talking about the pressure change, then what did we say? In liquid vapor, the pressure is constant. So when the pressure became constant, we said that the equilibrium has been achieved. So in the chemical reactions also, we have to understand at what point we will say that the equilibrium has been achieved. At what point we will say that the equilibrium has been achieved. One thing that you saw was that the concentration will become what? The concentration of the reactant and the product will become constant. Now, other way of looking at this will be, again, going back to the swimming pool example, the rate in which people are coming to swimming pool is equal to, please don't write this, okay, rate of in is equal to rate of out. Yes or no? Tell me, guys. This is what is happening in the swimming pool, right, Atif? Reba, yes or no?
Yes, sir.
Now, similarly,
Yes,
if I'm going from the reactant A to reactant B, and I will say that this is what? This is a reversible reaction in this way. Then when the equilibrium will be achieved, then I can say that if A is going to B, this is known as the forward reaction. And if B is going back to A, this is known as backward reaction. Okay, A to B is forward and B to A is backward, and hence at equilibrium, rate of forward reaction is equal to rate of backward reaction. Okay, this is one thing. Another thing is that the concentration of reactant and product will become equal or constant. The concentration of reactant and product will become equal or constant, guys?
Sir, constant.
Constant, okay? Constant, okay? It will become constant. Not necessarily equal. Not necessarily equal. Okay, not necessarily equal. Write this down. Let me know if you're done. Then we will plot both of these things in a graph. Okay, we will plot both of these things in graph. Please let me know if you're done.
done, sir.
Okay, all of you done? Okay, now let us plot the graphs here. So first of all, what we will do, we will plot the graphs of the rate. Okay, the rates are equal. Okay, that one. So let me say, first of all, there is a reaction like this. There is A, which is going to give you, let us say, B. Okay, A is going to give you B. And in this, we will have time here. As the time is proceeding, the reaction will proceed. And here we'll be writing the rates. Okay, here we'll be writing the rate. So initially, I would say, when we only have A, the rate of reaction will be very fast, right? The A will be getting converted into B. So the rate of forward reaction, okay, the rate of forward reaction is the rate of forward reaction, and this will be the blue will be the rate of backward reaction. So the rate of forward reaction will be very high, and slowly it will be decreasing, because what is happening? The concentration of A is decreasing. That is why the rate at which the reaction will be happening, it will also decrease, and it will get to some constant value like this. It will get to some constant value like this. Now, initially, the product is 0. There is no product here. That is why what will happen? There will be no rate. Okay, the rate will be 0. But essentially, as the reaction starts, what will happen? A, it will get converted into B. Now, B has a tendency to get converted to A also. So what will happen? B will also start getting converted to A. The rate of backward reaction will slowly increase, and it will increase, and it will reach till A, right? It will reach till A. Now, this is the point when both of the rates become equal. We'll see that this is where equilibrium has been established. Equilibrium. Okay, this is where equilibrium has been established. Now, this is the case when we were talking about rates and comparing the rates of reaction. We can also compare this thing with the concentration of A and B. So we can write here, this is the concentration. Here we will write the concentration. Okay, and here we will write the time. Now, essentially, there is some A which is there. And slowly the A is getting decomposed, and it is getting converted to B. Right? It is reacting, and it is getting converted to B. So its concentration will decrease, and then it will get a constant. Then it will get constant. Similarly, what will happen to B? The concentration of B will increase. The concentration of B will increase. And again, it will also get a constant value. Okay, it will also get a constant value. Now, the time at which it is getting constant, that is the equilibrium state. Okay, this part, here is the equilibrium. Now, whenever the change is happening, that is not equilibrium. Okay, and also, so let me just get this part here. Okay. Now, this is not equilibrium. Okay, let me just point this out. This is not equilibrium. Not equilibrium. Okay, here we have equilibrium. This is the state where we have equilibrium. Okay, after this point we have equilibrium, because the concentration have become constant. Okay, concentration will become constant, the rate will become equal. Okay, the number of the people in pool will be constant, right? It will be constant. So 5 people in the pool, 7 people outside the pool. The number of people, they are not equal, but the rate of in and rate of out, it will be equal. The rate of in and rate of out, it will be equal. Please let me know if you're done writing this.
When we're analyzing.
Done, guys?
Done, sir.
Okay. All right. Characteristics of equilibrium. Characteristics of chemical equilibrium. Characteristics of chemical equilibrium. Number one, chemical equilibrium is dynamic in nature. Chemical equilibrium is dynamic in nature. Chemical equilibrium is dynamic in nature. What does it mean? It means reaction does not stop. Okay, reaction does not stop, rather rather only the rates of forward and backward forward and backward becomes equal. Hence, there is no change in the concentration of reactant and product at and after equilibrium. Okay, this is the first point. The important thing is that it is dynamic in nature. What does it mean? It means that people are still coming in and they are still going on. It is not static. Okay? It's not like 5 people have come into the pool and they are not leaving the pool. They are leaving the pool, but new people are coming in the pool. Okay, that means it is a dynamic equilibrium. It is a dynamic equilibrium. Second point, the properties of system. The properties of system. The properties of system are constant. Are constant at the equilibrium. And remains unchanged after that. Remains unchanged after that. Write the next point. Anna, what is the property that we are talking about? We talk about mainly in chemistry, we talk about the concentration. Okay, but if there is gaseous molecule, then we will talk about pressure also, but essentially speaking, concentration and pressure. Okay, then what do we have next? The third point. Equilibrium can only be attained in closed system. Equilibrium can only be attained in closed system. Okay, why? Because for example, if you have an open system, then what will happen? Some of the reactants which get converted into product, those product are gaseous molecules. The gases will escape. Now, if the gases have already escaped, it cannot go back to the reactant. That is why we need to have a closed system for the equilibrium to be established. Okay, it can only be attained in a closed system. Right. The fourth point. Equilibrium can be achieved from any direction. Can be achieved from any direction. It means that if whether you are starting from reactants or product, doesn't matter. You will be getting to the equilibrium state wherever you are starting from. And the last point is the catalyst. The effect of catalyst. Okay. Okay. How many of you know what is the meaning of catalyst in general English sense? What is a catalyst?
Enzyme that fasten up the reaction speed.
Okay, you are talking about biology, enzyme. Yeah, fine. And so anything that will speed up the process, that is a catalyst, right? Yes or no, guys?
Yes, sir.
Something, yeah. So catalyst has something to do with time. Okay, it has something to do with time. Now, what will happen? Now, if I add a catalyst to the system, what it will do? It will get the reaction to achieve equilibrium faster. Okay, the equilibrium will be attained faster. It will be attained quickly, but it will not alter the equilibrium point. What is the meaning of equilibrium point? It means that if an equilibrium was attained at a certain concentration, then that concentration will not change. The concentration of reactant product, which is getting constant, that concentration will not change. Only it will be achieved faster. Only it will be achieved faster. That means you can write a catalyst does not alter the equilibrium point. Okay, what is equilibrium point? The point that defines where the equilibrium has established. Okay, the point that defines. Now that point will differ if you're using, for example, that can be pressure also. The pressure, what is the vapor pressure? It can be concentration also. Okay, but it does not mean that it is equilibrium has nothing to do with time. Catalyst has something to do with time. Okay. Okay. So catalyst does not alter the equilibrium point. Equilibrium point means the concentration or any property that becomes constant at equilibrium. Nothing to do with time. Done? Yes or no, guys? Done? Okay, all of you are done.
Done, sir.
Okay. Now let us look at a reaction. Don't write this, okay? Don't write this. Let us look at a reaction in which we have NO2. It is dimerizing into N2O4. Hence we need 2 moles of NO2. Hence we need 2 moles of NO2. Now, I said something about the rate of reaction, right? I said something about the rate of reaction. That rate of forward is equal to rate of backward. Yes or no? This is the criteria for equilibrium. Yes or no? Tell me.
Yes, sir.
This is the criteria for equilibrium. Okay, fine. Rate of forward, it is equal to rate of backward. So in rate of forward, what is the forward reaction that is happening? We have 2NO2. It is getting converted to N2O4. And what is happening in the backward reaction? We have N2O4. It is getting converted to what? It is getting converted to 2NO2. Okay, 2NO2. Now, for rate of forward reaction and rate of backward reaction, let us see how we can represent this in terms of some equation, in terms of some numbers which involves NO2 and N2O4. Here also NO2 and N2O4. These parts. Now, can I say that the rate of forward reaction, it will depend on the concentration of the reactant? If there is more reactant, that means the forward reaction will be faster. Yes or no? Tell me. Can I say that the rate, it is directly proportional to the concentration? Yes or no?
Yes, sir.
Yes, we can say that. No? The rate is directly proportional to the concentration. It is directly proportional to the concentration. Now, let us see these two reactions, that there are two NO2, which is combining, and it is forming what? N2O4, and we have N2O4, which is combining to form. It is dissociating to give you 2NO2, which is giving 2NO2. Now, whatever is the concentration of NO2, I mean, you will have NO2. Let us say if you have 0.5, let us say if you have 1 mole. Let us say we have 1 mole. Let us say we have 1 mole of NO2. 1 mole of NO2. Then what will happen? 0.5 mole from here and 0.5 mole from here, they will react with each other. Yes or no? Tell me. Yes or no, guys?
Yes, sir.
0.5 mole and 0.5 mole are reacting with each other. Okay. That means whatever the concentration is there, it is also related to the stoichiometric coefficient, right? It is also related to the stoichiometric coefficient, because when we are using 2 moles here, that means I can say the rate of the forward reaction. For the rate of forward reaction, this will be directly proportional to the concentration of NO2 into the concentration of NO2, because I can write this equation like this. Yes or no? Tell me. And for here, what I can say, the rate is directly proportional to the concentration of N2O4 only, because we have only one reactant. This is just like saying if you had, let us say, if I had A plus B giving me C, right? A plus B giving me C. That means what is happening here? We have the rate is directly proportional to the concentration of A. The rate is also directly proportional to what? Concentration of B. Yes or no? So I can say the rate is directly proportional to the concentration of A and the concentration of B. Yes or no, guys? Tell me that.
Yes, sir, we can.
We can say that. Same thing. Now, what I am saying, I'm just putting A and A here. So this will be A, this will be A. Then I can say that rate is directly proportional to the concentration of A square. If we have two of the react, I mean, same type of reactants. Okay, same type of. So I can say rate is directly proportional to NO2 square. And here the rate is directly proportional to only N2O4. Now here I can write rate is equal to some constant K into the concentration of NO2 square. And here I can say rate is equal to some constant K and N2O4. Yes. Now I will say this is K forward and I will say this is K backward. Is that fine, everyone?
Yes, sir.
Okay. Now rate of forward is equal to rate of backward. That means this rate and this rate will be equal. Hence I can say K forward, in which we have NO2 square, it is equal to the rate constant of backward into N2O4 Yes or no?
Yes, sir.
Yes, sir.
Yes. Now, what I will do, I will write K forward upon K backward. It is equal to N2O4 divided by NO2 square. Correct? Yes or no?
Yes, sir.
Yes, sir.
Now this is what, this is a constant, this is a constant, this will make a greater constant that we will call as the equilibrium constant, and which will be equal to the concentration of product raised to its stoichiometric coefficient divided by the concentration of reactant raised to their stoichiometric coefficient. Tell me, did you understand what happened here till now? You were with me, yes or no?
Yes, sir.
Yes, sir.
Yes, okay. हाँ, तो ये तो भाई साहब हमने बहुत ही खेल कर दिया आपके साथ. ये इतना जो है ना, I mean, if you start the NCERT, if you start anywhere, you will see they directly start with the chemical equilibrium, and they say that the equilibrium constant, it is equal to the product of the concentration terms of the products, the product of the concentration of the products raised to their stoichiometric coefficient, and the product of the concentration of the reactant raised to their stoichiometric coefficient. Okay, and this above part, it is not in your syllabus. Okay, what is the rate of forward, rate of back? I mean, rate of forward and rate of backward is there, but KF, KB, these things are not there. Okay, these things are not there. But you essentially got now how we get chemical equilibria and how we get the equilibrium constant. Yes or no? How are we getting the equilibrium constant? We started with here, that is rate of forward is equal to rate of backward, and slowly we came till this point, and we said, when we said that these two are constant, we will take this 2 constant as a big constant, that is K, and then we will get the equilibrium constant. Okay, now what I want to do, I want to show you guys that this works. Okay, this works. Okay, wait a second, let me just delete this. Acha, can you see this part, these things?
Yes, sir.
Yes, okay, fine. Now what is this? This is the initial concentration, initial NO2. Let me just do one thing. Let me also get this here, and here I will write the serial number. And what is happening here is that I'm doing different experiments. Okay, so in the first experiment, I had the initial concentration of NO2 as 0.142 molar. Okay, fine. Got it, guys? Yes or no? Tell me. And initially I had what? 0.NO2. NO2's concentration was how much? 0.142. Okay, initially. Then the reaction happened. Okay, the reaction happened. After reaction, what did I find? I will have N2O4 here. After reaction at equilibrium, I found that this concentration has lowered to 0.042. Obviously, it was reactant, so it will get lowered. And at equilibrium, the concentration of N2O4 was equal to how much? 0.10. You understand now what is written here and here? Tell me.
Yes.
Yes, all of you? Okay. So initially, when we have 0.142, I got 0.042 and N2O4 was 0.1. Then I took another, I changed my experiment, and in this experiment, I started with 0.2 molar. Then I got 0.051 molar of NO2 and 0.15 molar N2O4. Then I started with 0.3 molar, 0.4 molar, 0.5 molar, 0.6 molar. Okay, fine. Now I will see the equilibrium constant. Okay, that is K. I want to calculate the equilibrium constant. So what will the equilibrium constant for us be? So that the equilibrium constant for us, it will be equal to, and this should be constant over all the reactions. It should not change. It should not depend on the initial concentration, right? It depends on what the equilibrium concentration, right? Equilibrium concentration, and also the ratio of equilibrium concentration. So we have what? N2O4, and here we have NO2 square, right? Yes or no? Tell me. This is the equilibrium
Yes,
constant
sir.
for us. Okay. Now let me just give an equal to sign, and in the ratio that we will have this D2, and we will divide this by the concentration of NO2, and yeah, I also need to multiply this. So let me just put up a bracket here, and then I will have inside this bracket NO2 multiplied by NO2, right? So D2 is what? The concentration of N2O4, right? D2 is the concentration of N2O4. What is C2? C2 is the concentration of NO2 and again multiplied by C2. And so C2 square. That is the concentration of NO2 square. So this is what? 56.69, 56.69. Okay. Now I will just get this here. Now can you see that this value is constant? This value, these values are changing. What is D3? D3 is the concentration of D. अच्छा आप लोगों ने Excel use किया है कि नहीं कभी? Anyone who has used Excel? You must have learned Excel in school, na?
Yes,
Somewhat.
sir.
Yes,
है ना?
sir.
Cell will पता होगा आपको D1, D2, D3. Okay, fine. Thank you very much. So can you see that the ratio of the forward reaction and the back? I mean, the ratio of the forward reaction constant and the backward reaction constant, they are same, है ना? The rate constant of forward and backward, the ratio is same. So equilibrium constant, it doesn't matter what you are taking, whether you are taking 0.142, 0.2, 0.3, 0.5, 0.4 or 0.6, the equilibrium constant is going to be same. Okay, and this is very helpful. Now this is very helpful. Why? I will tell you why the equilibrium constant is very helpful. Let me stop sharing this.
Sir, will there always be slight differences?
हाँ, वो slight differences वो जो आपने देखा ना 56.69 then 57.29, that much. Those differences you are talking about, na?
Yes, sir.
Here, na? See these differences.
Yes, sir.
See, if I ask you to draw a line of 5 centimeter, will you be able to draw accurately 5 centimeter ever?
Only if you use a ruler, sir.
No, even if you use a ruler, will you be accurately 5 centimeter, not even a 0.00001 decimal point away from 5 centimeter? No, na?
No, sir.
Hana? So it depends on what measuring instrument we are using, right? So we are just confined with what measuring instruments we are using. So whatever you are seeing the difference now, that is due to the measurements, nothing else. For nature, it is constant. If we had an instrument which had the uncertainty of, I mean, it had very small uncertainty, then our values will also look good. Our values will also look good. Okay. Fine. So where did I start? Well, yeah, I started with yes. So we had K, it is equal to whatever the product is there, the concentration of product raised to their stoichiometric coefficient divided by the concentration of reactant raised to their stoichiometric coefficient. Okay, raised to their stoichiometric coefficient. Now please remember this K, it is only for the equilibrium. Okay, the equilibrium concentration of product and the equilibrium concentration of the reactant. At that point, we define the K equilibrium. Okay, this is the K equilibrium, the equilibrium constant. The equilibrium constant. Okay, so we will be learning about equilibrium constant, more about equilibrium constant. What type of, there are two types of equilibrium constant. If we measure the equilibrium constant in terms of concentration, then we write it as Kc. If we do it in terms of product, we write it as Kp, and so on. Okay, so these are different things that we will learn. Today was just a formal type of introduction to equilibrium, just to let you guys know what we are going to do. And one thing, please keep in mind, we will be always doing ICE, the initial condition of the system, then we will change something, then we'll tell about the equilibrium condition of the system. Okay, fine. So till now, please tell me if there is any doubt about equilibrium, about thermodynamics, or anywhere in the chemistry syllabus that you are going in school, or if you're self-learning. And if you have any news about your examinations, please tell me about that also. Nothing. कुछ नहीं हो रहा है. Yes, Mohammed.
Our exams will be on February.
February? Like which
The
week?
last
February?
week. Last week maybe.
Last week maybe. Okay, fine. Acha, We have some chapters. I wanted to talk about those chapters. For example, by 10 March, the new academic year should start. Okay. 10 March is very early. Okay. So we are left with equilibrium, S block, P block, hydrocarbons. No? So equilibrium is left 1, S block 2, 3, and both chapters are left right now. Okay.